Gators. This is 6.2, Approximating Areas with Riemann Sums. Let's take a look at this graph, and it does not lend itself to using geometric formulas, and I'd like to show you something other than counting squares. What we want to do is we want to find the area between 2 and 6, and I'd like to show you another method to find this area that doesn't involve counting squares, and this will be called a Riemann sum. All right, so let's take a look at this curve right here. It's a parabola, and we would like to find the area under the curve from 2 to 8 using 3 subintervals. So I drew the 3 rectangles. The way I found the width is I took the length of the interval, which is 8 minus 2, and I divided by 3, so that was 2. So each one of these widths of the rectangles is 3. And I chose the left side of the interval, the left x coordinate, so that I could find the function. So I'm going to choose f of 2, and f of 2 is the number 6, so the area of the first rectangle is 12. I'm going to use the left side of this next interval, which is f of 4. f of 4 is 8, so this is going to be 16. And again, I use the left side of this interval, which is f of 6, and this is going to be 6, and that'll be 12. So when I add all of these up, that's going to be 40. Now, I wrote a summation notation. I'd like you to get used to that. And what it is each time my input value changes, so 2 times k, so if k is equal to 1, the first time it'll be f of 2 that I use, then k equal to 2, this will be f of 4, and k equal to 3, then this will be f of 6. So this is shorthand notation to show the sum of all of these areas. Let's take a look at a right Riemann sum. And again, our interval is too long, but this time instead of using the left x-coordinate, I'm going to use the most right x-coordinate and use its y-coordinate. So this is going to be f of 4, and then f of 4 is going to be 8, and the width is 2, so that's 16. Then the next interval, f of 6, and f of 6 is 6. 6 times 2 is 12. And then the f of 8 happens to be a height of 0. That's going to be 0. And so this will be 28. And again, I wrote this summation notation. And notice that this formula will create the 4, 6, and 8. So when k is equal to 1, this creates a 4. When k is equal to 2, it creates a 6, and then an 8. Let's take a look at the midpoint Riemann sum. And the midpoint Riemann sum is I would take the rectangles, but the height is now dictated by the midpoint. So in this first interval, the midpoint is 3, and f of 3, when I put it into my function, is 7.5, which will create an area of 15. The midpoint here is 5, so f of 5 is 7.5, that is also 15. And in this next interval, the midpoint is 7. I'll put a 7 into the formula. That'll be 3.5. That'll be 7. And so this area will be 37. And again, this summation notation creates all of these input values of 3, 5, and 7 as k goes from 1, 2, and 3. Let's take a look at our last method, which is the trapezoidal sum. And the trapezoidal sum is not formed by rectangles, it's formed by a trapezoid. And the trapezoid, the bases are standing up, and here is the height. And the height is our delta x, and our delta x is still the number 2. So it's kind of a sideways trapezoid. This is the formula for a trapezoid. It's 1/2 the height, and remember our height is this delta x, and base 1 plus base 2, and the bases are really the heights that right here. So our first trapezoid was 1/2 f of 2 plus f of 4 times delta x, and I'll reserve that. And then the area 2 will be 1/2, the bases are f of 4 and f of 6 times the width, 1/2 the height of the bases, and it happens to be that f of 8 is 0, so it's going to collapse to a triangle delta x. Now before I find each individual, and I notice there's some commonalities. I notice that each one of the formulas has a half, and each one of the formulas has a delta x. So I'm going to pull those all out, and then I'm going to do the sum. And I notice that there's some doubling of the in-between values here where the sides of the trapezoid were shared. Those are with a doubling. And so now I'm going to put in the numbers, and this is a 2, f of 2 is 6, f of 4 is 8, and doubling that, that's going to be 16. F of 6 is 6, doubling that, that's 12, and f of 8 is 0. And when I do some reducing, the answer ends up being 28 plus 6 is 34. And that's how I figure out the approximation of the under the curve with trapezoids. Let's talk about how do we determine whether they're an overestimate or an underestimate. When you have an increasing function, if you're choosing the left point on every interval, the rectangles are going to lie underneath. So this is going to be an underestimate. When it's an increasing function and you're choosing the right x coordinates to determine your heights, you're going to have an overestimate. And a decreasing function, if you're choosing the lefts, you're going to find that every rectangle is above. So this is going to be an overestimate. And when you're choosing right on the intervals each time, you're going to find that the rectangles are lying underneath. So this will be an underestimate. Let's take a look at trapezoids. When we're looking at trapezoids, you're going to find that when it's concave up, all the trapezoids lie above the curve. So this is going to be an overestimate. And when it's concave down, all the trapezoids lie underneath, and this will be an underestimate. Let's take a look at a trapezoid versus a midpoint. Here is a trapezoid where the ends of the trapezoid are the ends of the interval here. Let's take a look at a midpoint. When we have a midpoint right here, and I draw the tangent line, this is the tangent line right here. What's created is two triangles, and these triangles are congruent. So this triangle right here that's sitting above the tangent line is the same as this area right here. And if I redistribute the area and take this and put it up here, I'm going to have this picture. It is also a trapezoid, but it's not the trapezoidal rule. It's determined by the tangent line that's lying underneath. And when this happens, this should show you that the midpoint estimation will be an underestimate for concave up. So because it's based on the tangent line and it's concave up, this will be an underestimate. When it's concave down, the tangent line lies above, and so the trapezoid that's formed by redistributing these triangles will be an overestimate. Let's take a look at Riemann sums using a table. And so here's a kind of a quick graph of the table. I think I needed one more, and it looked like they were all increasing here. So I'd like to figure out the right Riemann sum. Right Riemann sum means I would be taking a look at every interval and looking at the, here's this interval here, and I would be looking at the right. And this interval I'd be looking at the right interval, right, and then right. These are all right Riemann sums. So I'd be looking at the height, which is 13, and timesing it by the width, which is 3. And then the height, 18 times 3, and the height, 23 times 3, and then 27 times 3. And I go ahead and put in the calculator and find the estimation of my area. And then this would be in, remember it's gallons per minute, and remember we're multiplying times minutes, so the answer will be in gallons. And let me go ahead and put that in the calculator very quickly. And that'll be 39 plus and I'm getting 243 gallons. Now the question is this approximation greater or less than the true value? Now remember, I'm using a right, and right means that my rectangles are going to be sitting above, so this will be an overestimate. Okay, now let's take a look at a left Riemann sum. Left Riemann sum would mean that I'm going to be using the left points here. So I'll be using all of these points here on the left side. So I'm going to be looking at something like this on the left side. On the left side. And so then I'll be using the height, 7 times 3 plus 13 times 3 plus 18 times 3 plus 23 times 3. And again, my units will be gallons, similar, multiplying the two units. And so that'll be 21 plus 39 plus, and I'm going to get 183, and this will definitely be an underestimate because it's lying underneath the function. Let's take a look at the same thing and look at midpoints. Now this is for two intervals. I've got to look at this interval and this interval. I've got to have an interval so that I can use a midpoint here. So I'm going to be using my midpoints here to create my area here, my midpoints right here. And so I'm going to use the 3 and the 9, and that'll be 13 will be the height, and the width will be 6, and the height will be 23, and the height will be 6. And again, this will be in gallons when I multiply the two units together. So that's 13 times 6 plus, and I'm going to get 216 gallons. Now, when I use the trapezoidal rule with 4 subintervals, then remember that I'm doing 1/2, and each time, let me go ahead and draw it. What I'm doing is I'm doing a trapezoid every time. So every time I'm doing a trapezoid like this. And so I'm going to do 1/2, and I know that my width is 3, and then I'm going to do a height of 7 plus 13 plus, and then I'm going to repeat it 1/2 times 3, and this time my heights will be 13 plus 18 plus 1/2 times 3, and this will be 18 plus 23 plus 1/2 times 3, and then this will be 23 plus 27. And you can kind of pull everything together, 1/2 times 3, and then 7, and then there's just 2 13s, which is 26, 18, that's 36, and a 46 plus 27. And we can make our lives a little easier by doing that. 1.5 times 7 plus 26 plus 36 plus 46 plus 27, and we'll get 213 gallons right here. And this is the end of the screencast.